too, David, if you don't know all the content off the top of your head? And the answer is, I ask people to help me. And so I've some very nice people who have given me their gone into my uni for me so I can have a look at the resources your lecturer has, and we can have a look at some stuff. So the requests I've had are for topology, in the sense of open sets and stuff like that, and also for continuity and differentiation out of piecewise functions. And I feel like I need my brain to have a little longer to think about the topology, so I'm going to talk about that question first and have a look at this question from one of the tutes, just to have a handle on it, possibly do a slightly different one. This practice question, well, it's a tute question, but yeah, I'll just run with the one that's here and I'll just see how I go. I just want to make sure I'm doing it, and even if it's something you've seen before, I just want to try and make sure that you can see how I think about it as someone who's, probably not going to pass this exam if I went into it, because I haven't done the course. So you can try and get a handle on how someone might attack it. So let's have a look at okay, so if you have other questions about this as we go along, feel free to ask them, and we'll try and make sure that we talk about them. So we're just going to start with an example problem and see how we go. Aren't they the same question? Oh, interesting. Okay. Well, I'm just going to make one up. Like, I just want to... Okay. So this is a function. And what we're going to do is we're going to decide if it's differentiable. And f is actually, yeah. So we'll give that a go, just so we can get a handle on the definitions of these things. So that means I would need a definition of what these things mean. So if I go to a computer and have a look in the notes that Ray has given you. No, that's not how that works. This is a limit, okay. Let's see, be a limit point of A. What does limit point of A mean? That was back in topology, was it?
So it means that for all sequences that are in the domain.
Right. Now, a limit point is one where there is a sequence that goes there. Yeah, we don't care about that. Okay, cool. Right, so there is a sequence of points that none of which are equal to that approaches it. Oh, okay, so we sort of have limits for sequences, and then we use that to define a limit for... That's interesting.
We use that because we can talk
Mm-hmm. Okay. Yep.
So that's just, but if you had like a set which was a union of disjoint points, there's no limit points anywhere in that set, like the natural numbers. So
Okay.
you can't really define the limit of a function on a set like that. You need like a...
Yep. I will process that in a minute. So your lecturer has set up what limits mean, and he's got a theorem that's saying that limits in this sense here is the same as limits for every sequence goes there. Okay. And then properties of limits that we're familiar with. Squeeze theorem. Oh, this is new. Alright, so basically if one function is less than another function, then the limit of one has to be less than the limit of the other. Well, that sort of makes sense, I suppose. So we say it's continuous if for all epsilon greater than 0 there exists a delta greater than 0 such that for all x in A, if the distance between x and c is less than delta, then the distance between f of x and f of c is less than epsilon. So that's the same as saying that the limit exists, right? Yeah.
Yeah, if we're
Yeah.
have points that are just limit points, then it's saying that the limit of the function is the value of the function c.
Okay, so this theorem, if it's continuous at a particular point, then the limit of the function goes to that point. Cool. For every neighbourhood, what's a neighbourhood?
It's just, it's an epsilon neighbourhood. So
Oh, all right, that's okay. Cool, I understand that. So an epsilon neighbourhood, there exists a delta neighbourhood such that, oh, well, that's just a restatement of the definition. For every sequence, that sequence can, okay, cool. We can build new continuous functions out of old ones. Okay, well this is about the definition then, right? I think we've gone far enough to get what we need for the thing we want to do. So is it continuous? So presumably continuous on a set is the same as being continuous at every point individually. Okay, so for A, to be continuous at every point of its domain, right? Okay, so I think I'm allowed to say that I think I'm allowed to say that polynomials are continuous without proving it.
we know that like the y plus x is continuous, as we did in lectures, but then we have the combining.
Yep. Cool. Okay. So if the point, like suppose x is less than 0, then f of x is x, which is continuous at x. So suppose c is less than 0, then f of x is x, which is continuous at c. I don't have to prove that because it's just done. Okay. And now we suppose c is greater than 0, then f of x is 2x, which is the product of two continuous functions, because a constant is automatically continuous because it's constant. And so is continuous. So the question is, what about when C is 0? And that's what you're wondering about. Okay. Well, I'm going to have to use a theorem or a definition, or probably the definition. So let me have a look at that list again. First, let me try and remember that list again. So for for it to be continuous, the limit of f of x as x goes to 0 has to be whatever f of 0 is. So I should write down what f of 0 is. Okay. I won't put the back on the screen because it's not that edifying to see that. So okay. Okay, or so there's the definition which has the epsilons and the deltas, or all the sequences in the domain that go to 0 go to, the f of those go to 0. I think that's everything on that list. Oh, and there's the neighbourhood thing. Okay. I'm just going to use the definition. So I need to show it's continuous at that point, which means I need to show that for all epsilon greater than 0, there exists a delta greater than 0, such that whenever x minus c intersection A, whenever the distance between x and c is less than delta, then the distance between f of x and f of c is less than epsilon. Okay? So I'm just going to think about this. This is 0. And I know what it looks like as a graph of a function. It's x here and it's 2x there. So it's steeper on this side than it is on that side. And when I'm very close to 0 here, then I need to show that no matter how close to when I'm very close to 0, then no matter how, then I can get, yes, sorry, however close to 0 I want to be on the y-axis, I can create a distance that gets me in the right spot for on the x-axis. Okay, so let epsilon be greater than 0, right? Because that's the rule, like for every epsilon. Yep. And then what we like to show is that there is a delta that will make sure that f of x minus f of c is less than epsilon, whenever x is less than delta. Okay. So our goal is to say, therefore, like that. That's the last thing I want to say, because then it's continuous. But in the middle here, I might not have enough space. I have to tell the reader what the delta has to be. So this delta is going to be equal to something, and I'm going to fill that in a second. Don't know what it is yet. Because, if I want... So I might need more space. But that's what I'm going to say at the end. So suppose this and that. So I guess, damn it, I'm out of practice, so I can't necessarily write the right amount of space. Let delta be that, and suppose x minus 0 is less than delta. And then we say, therefore, f of x minus f of 0 is less than epsilon. Okay. So if we can show that there is a delta such that when we have this, it produces this result, then it's continuous at that point. So let's see. Okay, well that's just the same as the absolute value is less than delta. So if x is positive, then we have that x is between 0 and delta. Yep. Which means that 2x is between 0 and 2 delta. So fx is between, the absolute value of f of x is less than 2 delta, because that's what f of x is there. Okay, and if x is less than 0, that means that this, because the absolute value is less than delta, it must be between minus delta and 0. And if x is in that zone, then that is f of x, right? And so therefore the absolute value of f of x is less than delta. Okay, so if delta was half of epsilon, we'd be good, because it would cover this one and this one at the same time. So if delta was half of epsilon, then when I get to epsilon on 2, and I get down here, that's epsilon, right? So f of x, the absolute value of f of x is less than epsilon. And when I get down to, and here, well, that's equal to half of epsilon, which is less than epsilon. Which is also less than epsilon, because it's half of epsilon. Okay, and so therefore, the absolute value of f of x is less than epsilon, and therefore this is less than epsilon since f of 0 is 0. That worked out well. Yay. Now I don't know what I would do if it, because I can imagine it might not be this simple. Like if this answer was not 0, if the answer for f of 0 wasn't 0, it might not be quite so easy. But I could try it. So what I did was, I knew that my function was different on either side of 0, so I considered those cases separately, and each of them gave me information about where f of x was based on the delta, and so I chose my delta so that this came out to be less than epsilon.
So regardless of which f you choose to use, it's still going to be less than epsilon?
Yeah, so this one is less than epsilon, and this one's really less than epsilon, but it works for both. It works for the one that's bigger, so it works for both. Yep.
And can you go right back to the picture? Just so it's kind of nicely drawn in there with the yellow rectangle at the top, the top one.
Yeah.
So you can see that the largest that your delta could be for a given epsilon has to be at about, it's going to have to be like epsilon or 2.
Yeah.
Because that height epsilon is twice.
It's twice this distance, yeah.
You know that if you chose that, it's going to work for the other one because it's going to be a smaller.
Yeah. Because the actual, if I copy this distance here, that's, the box is bigger. Yeah. I did quite well, didn't I?
So that one of the intuitions that Ray gave us was that the function enters, you want the function to enter through like the side of the box that you made and exit through the side. You don't want it to exit through the top.
That makes sense.
Through the top or the bottom, it's bigger than the epsilon. Right?
And it's allowed to go through the corner because that's just the right one.
That's equal to epsilon.
Okay, so this distance was epsilon here. And based on that epsilon, I can pick this delta for this, and actually it's this one actually happened. That epsilon happens here, so it's this delta for this. No, that doesn't make sense. No, that's okay. The idea is that if I choose this epsilon for this one, then the delta I need is this one. So if I choose the delta to be smaller, then it's still okay. Yeah. So this is a better picture of my proof there. I chose the delta based on the epsilon there to make it work, and I confirm that still works for this one because it's inside the zone I want. Yep.
So alternatively, when you had the x minus 0 is less than delta, you could sort of just that one there. You could just multiply both sides of that inequality by 2. And so you would get 2x minus 2 times 0 less than 2 delta. And you're getting something that is now something. So that's what I think you would do if you didn't have it at 0 there.
Well, that's all right. I mean, so you're saying that we could have arranged, knowing that x is less than, the size of x is less than the size of 2x, we could have done that, maybe. Anyway, I'm going to do the continuity bit, like the differentiability bit. I know it's not differentiable because there's a kink in it. Some of them are differentiable, even if they have different functions on either side. I know it's no. But let's see. The definition of differentiability, I didn't get up to. I'm going to need to know what that definition is. In Maths 1, in first year, I don't think they have that in first year anymore, but it used to be that the definition was that the derivative, which was a limit of its own, existed at that point. But I'm just going to get to finding out about that.
So it's in the next section.
That's in the next one. Suppose that f which sends a to r is a function where a is non-empty, interesting, and contains no isolated points, also interesting. Then we say f is differentiable at the point c if the limit exists, in which case we say that limit is f dash c. And it's differentiable on a if it's differentiable for all a. Okay? And so classic functions like polynomials would be differentiable, and I don't think we need to prove that. It would be okay to say that x is differentiable, because f of x minus f of x is x minus c over x minus c, which is always 1, and so that's okay. Okay, cool. So just going back. So we actually would have to calculate that limit. If and only if there exists, well, just a second. There's another theorem here. Suppose that f is a function and c is a limit point of a, then f is differentiable at c if and only if there is another function such that rf of c is 0. The limit of c as x goes to c as rf of c is 0. No, I don't know how that's helpful. I'm sorry. We're rearranging this formula.
Yeah, it's writing it as a linear approximation.
Oh, fun. Okay. Okay, and then that's all the classic stuff. That's all right. So we have to use a definition. There's no theorems that go with showing that it's continuous, as far as I know, other than combining them together. So we can do the same trick before. C is less than 0, then f of x is the same as x, which is continuous at C. And it's basically because there is an open set around C that's completely contained inside the set that I'm talking about. And suppose C is greater than 0, then f of x is 2x, which is the product of two continuous functions. No, not continuous, differentiable. So it's differentiable. Beautiful. I just put apostrophe-able. Remove letters, put an apostrophe. And now we're going to suppose, we don't need to suppose c equals 0, but it just fits with the pattern. So we're going to try and show it's continuous at c, which is 0, not continuous, differentiable at c, which is 0, which means we're going to have to try and figure out what the limit, so we need the limit as x approaches c, which is 0, of f of x minus f of 0 over x minus 0 to exist. That's what we need. Okay, well, a limit we've discovered is a point such that, however close to this point 0 we are, this function is close to that limit, like from an epsilon and delta point of view. And also, there would be sequences, or if the limit exists, then the limit of any sequence, like this calculation acted upon the x's in a particular sequence, would have to go there too, right? So it occurs to me, I know from the way I think about limits that when x is positive, this thing is the derivative of 2x, which is 2. And when x is negative, this thing's the derivative of x, which is 1. And so if you do the limit restricting yourself entirely to positive x's, you get a different answer than if you do the limit restricting yourself entirely to negative x's. But technically, you don't have in this course a definition of limits from above and limits from below, which is distressing. So we can't do that in this course.
In section 4, they define a limit which is very similar to the continuity.
Okay. Is that here, in this thing? Is it summarised in this?
Start of
Section
section 4.
4. Oh, so is it in this list? Yeah, that's the definition of limit, but there's no such thing as a limit from above and a limit from below. Okay, but, I do know that all the sequences should work, right? So if I can think of a sequence that the sequence goes to different places, then that would contradict the theorem that says that all the sequences go to the same place if the limit exists. So I can do it via sequences, and that'll be okay. So that's what I could do. If I know in advance I'm trying to show it's wrong, so I could show that. With that sequence, then f of xn over xn is 2 1 over n times 1 over 1 over n, which is 2. And so therefore fxn over xn goes to 2 as n goes to infinity. And consider, I'm going to be sloppy and use the same symbol for xn if that's okay. I really shouldn't. Dashed, there we go. Oh, that's distressing because we've got derivatives as well. Star, nice. Okay, and so f of xn star over xn star is minus 1 over n over minus 1 over n, which is 1. And so therefore f of xn star goes to 1 as n goes to infinity. Now, if this limit existed, they would all go to the same place. That's what the theorem said. Just let me check just a second. It was here. Oh, here we go. Then the limit is L if and only if for every sequence such that xn goes to C, f of xn goes to L. Okay. So, when we go back to this, so we should actually say here, so xn goes to 0 and also, so xn star goes to 0 and also, though this, so since f of xn goes to 1 and f of xn star goes to 2, with 1 not being equal to 2, the limit of x goes to 0 of f of x over x does not exist. Right. I don't know if that was the best way, but it was the first thing I thought of. Oh yeah, yep, gotcha. Yep. Because if it did exist, they would all go to the same place. That's all I can think of at the moment. I can't think of a better way at the moment, because at the moment the set of definitions and theorems that we have doesn't include the thing I would normally do. Because what I'd normally do is say, well, if x is greater than 0, then this limit is this, and if x is less than 0, then this limit is this. But we don't have a theorem that sort of specifically covers that, so I had to go via sequences. And that's not too bad an approach to go via sequences, because the limits tend to work out the same way anyway. Yeah. And it looks like, I'm guessing that at this stage in the game, we're allowed to just, when we look at something and go, oh, that just goes there. Especially if it's constant, you can always know where it goes. I guess if you had something that was x squared on one side and x on the other side wouldn't be just a constant anymore. But you could still argue that it goes to 0, I reckon. Okay, so this is I don't know if there is this is our new version of one-sided limits. We just have to do it via sequences these days. We could probably have tried to do it via the definition of the limit existing, but I have an answer now.
So why even so doesn't the theorem of limit work for, because you've got f of xn divided by xn, and that goes to 1, and then, yeah, so, but the theorem says that just take f of xn and goes to a sequence. There goes to a
Yeah, the f, this is the f, because we want this limit to exist. So the f in the definition of a limit is actually all of this. Yeah. So if you wanted to make it feel like it was more like the definition, you could say let g of x be this calculation. And then it might make it a little easier to write. Yeah. So I'm the sort of person in this exam who's going to be using a lot of that scribble paper. Do you know if he's going to give you exam book with spaces to write in, or if it's just going to be one of those blue books that you just with lined paper, so you can take up as much space as you want? Good. That's good.
That's the sort of method that Ray has shown us to tackle it as well.
Oh, really?
Yeah, just pick a sequence with like 1 on n, or 1 on n plus something, and you know that the 1 on n always goes to 0, so you can pretty much make any sequence converge to what you want. And then
Nice.
go from there.
So if it switched over at 1 instead of 0, You go like 1 plus 1 on n and 1 minus 1 on n.
Yeah.
Yep.
How did you know what sequence?
I just wanted something that I knew went to 0, and I know that 1 on n goes to 0.
It goes like 1 n squared.
Yeah, I could have chosen something else, but that's how.
So you choose a sequence to converge to a specific limit that suits the context.
Yeah, because the theorem says that you need the xn to go to the c that you're thinking of. So my c was 0, so I thought of that. So I think it's useful to say that it should usually work that if it was at x equals c, I'd probably choose, xn to be c plus 1 on n, and the other one to be c minus 1 on n, because they would both go to the place I want, and one would maintain wholly on the top, and the other one would be wholly below. And so, yeah. So this is our new version of one-sided limits in real analysis. It has to be done via sequences, because that's the game that we're playing. It's a little bit like playing chess, only, and someone saying, no. Knights don't do this. Like, knights don't jump from here to here, they go here and then here. Suddenly change the rules. It comes out the same, but it just takes a little longer. Okay. Gosh, that would make chess so much harder if you had to remember where it had gone on the previous move. Oh, there's an interesting game. It takes 2 moves to get any chess piece to wherever you want it to go.
Determine where you want the chess piece to go.
I don't know. Like, if you move a knight, then you have to move the knight on the next turn as well. Not that I like doing that to chess because I don't actually enjoy chess. It's much more fun to play with the rules than actually play chess. Okay. So I think, how do you feel about that?
Pretty good.
Yeah? That's good. So just waiting until you had something else to say, just in case you did.
It's not too much of a trouble. Maybe could you go over the step function?
Oh, yep, let's do the step.
That's not differentiable at 0?
Well, it's not continuous, so isn't there a theorem that says if it's not continuous, then it's not differentiable?
Yeah. Which function are you talking about?
Oh, the one that was in the tutorial. The one that was 0 on one side and 1 on the other. This one here.
Yeah.
So since that function isn't, you would probably have to prove it's not continuous, but yeah. So yeah, if it's not continuous, it can't be differentiable, and I think there's a theorem that proves that. And that's because if it isn't continuous, you can arrange a sequence on one side to go to one place and a sequence on the other side to go to a different place. And so it's not continuous. Like, yeah, it can't be differentiable either. Cool. Okay. Good. Good. Any other thoughts or questions about continuity and differentiability before I move on from it? Rolle's theorem. Rolle's theorem. Did you know that Rolle's theorem, when it was originally proved, only applied to polynomials? Because Rolle didn't believe in any functions other than polynomials. And he didn't believe in derivatives either, so it wasn't done, Rolle's theorem wasn't done with derivatives either. So, yeah. But he still deserves credit, because it's the same idea. Okay. All right, well, I might leave that there, and maybe I will talk about the topology stuff, which has a very small number of theorems and definitions, but feels bigger. Topology in R, I'm going to say that because technically topology is bigger than that. I presume we have a whole course with topology in the title in third year or something. So my understanding of topology, in my vague memory of it back in the day when I studied it, is that the general study of topology is about the study of sets rather than individual numbers. You can begin by talking about distances and how far apart things are in terms of distance, and then you can create sets about how close together things are. And topology is the study of those sets of things that are close, as opposed to the study of the distances themselves. That's my understanding of it. So it's about closeness. So topology in R is about distances because you can tell exactly how close things are. You can subtract them, and that's how far apart they are. In the later study of topology, you remove the distance and you just keep the sets. And you say that two things are closer together if they're contained in a set that's contained in the bigger set. So, yeah, it gets a bit vague. But we're very precise about it. That's what mathematicians like to do. We're precise about vague things. Statistics is the ultimate in that. Okay, so we're interested in the distances between things. And so the big idea in real analysis that sort of everything is based on is that that's the distance between x and c. And I don't know if that's helpful, but it's useful for me to be able to say that as the distance between things, and it helps me make sense of stuff. And then we can talk about the neighbourhoods of certain distances around a point. So let's see. If this is c, and this distance is epsilon, then this set here is the neighbourhood of this radius epsilon centred at C. Is that the idea? That's the notation that the lecturer is using? Yep. He uses the wrong epsilon, but it's okay. Just a second. Right. Just had to write, the C was just getting worse. Okay. Okay. But it's actually just, it's the strictly less than. It doesn't include these endpoints. It's like that. Right. So which is the set of x's such that the distance between x minus c is less than epsilon. Like that. Which is the interval from c minus epsilon to c plus epsilon. Yep. They're all the same thing. Okay. So, the idea is that open sets are kind of nice because you don't run into issues of hitting the end of them. If you travel along this way and you stay entirely inside this set, you can never hit the end, because no matter how close to the edge you get, there's always a few more points that are a little closer. And so, in that sense, it's so interesting that you call them open, because in that sense it's like you actually can't get out of them, so that would make them closed in my head, but anyway, ignore that story. But they're sort of inescapable if you want to, like, yeah. But really, the idea of an open set is that as far as, no matter where you are in it, you can always move a little bit and still be in it. There's going to be some distance you can move that maintains you inside the set. Whereas a closed set, some of the points at the edge, you'll be able to move and you'll fall out of the set. Well, a not open set. So, for example, okay. So that's my understanding of it, but the definition, I'm just going to write that down. In an open set, you can always move a little and stay in the set. But if it's not open, there are some points where if you move a little, no matter how little it is, you fall off the set. Okay. So, the definition is that, and this is the picture in my head, if you have an open set, then no matter where you are in the set, you can always choose an open, like a neighbourhood, an epsilon neighbourhood that's completely inside the set. So if you're here, that's great. If you're here, it would be about this big. And if you're extremely close to the edge, zoom in with a magnifying glass. If you're very, very close to the edge, you can still find one. That's the idea. Right. So you really only care about one side of this. The other side doesn't really matter. It's the side that's near the edge. But the definition of it doesn't require you to be able to perceive where the edge is. Because the mathematics doesn't know that there's an edge. We can only see that because we draw the picture. Yeah. So the definition, set A is open when for any x in A there exists an epsilon greater than 0 such that the neighbourhood of epsilon contained in X is completely contained in A. That's the definition. And I'm just going to check if that's what the definition says on this piece of paper here. Yeah, good enough. Okay. So there only has to be one epsilon for that to work. So each x only needs one epsilon to do it. And so what that basically means is that an open set is made by layering on top of each other a whole lot of open intervals. Yeah. Okay, so the classic proof is, can you prove that an epsilon neighbourhood is open? And that's the classic one. Yeah, because I can do that proof. But are there any proofs of openness that were distressing? Sorry, that one? All right, let's do an example proof.
Like that.
Okay. So here we go. Prove that an epsilon neighbourhood is open. Okay. Let's go. So, we need to prove, well, this is a picture here. That's an epsilon neighbourhood. We need to prove that no matter where we are in an epsilon neighbourhood, there's an even smaller epsilon neighbourhood that's completely contained inside it. That's what we need to prove. Okay. So consider, we shall call it A, which is going to be an epsilon neighbourhood around the point C. Okay. And the definition says that no matter which x we pick, we have to be able to find an epsilon such that there's another epsilon neighbourhood that's even closer. We're going to have to change letters. We're going to have to use a different letter than epsilon because we've already used it. But that's okay, we can cope. We're allowed to use delta in this spot. There's nothing stopping us changing the name of the letter. So that's all right. So that's our first thing that we have to deal with. So we're going to have to say, let x be in A. Somewhere along here we're going to have to tell the reader what delta is. And at the end we're going to say, therefore, the neighbourhood of delta around epsilon is completely contained in A. And you say, therefore, A is open. But somewhere in here I have to tell the reader what delta stands for. Okay. Cool. We could possibly say suppose instead of let. Doesn't really matter. I like the charm of let. It's like X wants to be A, so we'll let it be A. that's sort of, I find that kind of charming. I want it to be A. Sorry. Okay, I want it to be in A. Cool, we're going to have to tell the reader what delta is, which means we're going to have to construct delta out of the letters we have so far, which so far we have defined epsilon and c, we should say for, oh no, this doesn't even make sense if epsilon isn't greater than 0, so that's sort of an assumption. But we're going to say epsilon greater than 0 and c in R, just so that, we've said what all the letters stand for. Okay, I'm supposed to say what the letters stand for. So the letters we have so far are X and E and C, and so if we want to tell the reader what delta is, we have to use some or all of those. Okay, so X is in A. Let me just draw this picture. There's C. This is epsilon this way and epsilon this way, and that's the edges of A there. And X is one of these numbers, and we want to try and fit an open interval into that space. So it seems to me that I need to fit it here, so the radius of this is going to have to be less than this distance here. So whatever that distance is, that's like c plus epsilon minus x. But it's going to be similar on this side, but the calculation is going to be different if I'm down on this end. So I might have to do it separately at each end. I might be able to do it with some absolute values if I'm careful.
You could do it with the minimum, like the minimum of...
Yeah. Oh yes, so I could put one like this big and one like this big, and one of them fits in. Like this one's radius goes down to the bottom end of C, and this one's radius goes up to the top end of C, and there's two of them and one of them fits in. Yeah, that's cool. I like it. So let delta be the minimum of the distance between X and C plus epsilon, and the distance between X and C minus epsilon. We don't actually need absolute values on them because we actually know, I just need more space. So C plus epsilon minus X and X minus C minus epsilon. So C plus epsilon is more than X, so if we go bigger number minus smaller number, that gives me the distance. And C minus epsilon is less than X, so if we go bigger number minus smaller number, that's the distance. So this is the distance to the top edge, to the right-hand edge, and this is the distance to the left-hand edge. Okay, cool. All right. So if delta is the minimum of that, then we have to show that n delta x is contained in A. And the only way I know to show that one set is contained in another is to show that every element of the other set is in the bigger set. So we should now say this, and then do some working and say, therefore, y is in A. Because that's how you show that one set is contained inside another set. All right, well, to be in A, that means the distance between y and c has to be less than epsilon. So we should calculate that distance. But to be in this one, the distance between y and x has to be less than delta. Right? Cool. So if I want... Okay. Well, let's see what happens. It seems reasonable. And we want to show this is less than something. I may need to make it less than half of... Oh, I don't know. Let's just see what happens. I'm going to need more space, I'm sorry. If I was in an exam, I would probably say 6 star on the next page. Okay, so this would be y minus x plus x minus c. Which by the triangle inequality is less than this. Don't know yet. We do know that x minus, the distance between x and c is less than epsilon, because x is in this set. Okay. So that's less than delta plus epsilon. Like this is less than delta and this is less than epsilon. That's what being in A means. The distance between x and c has to be less than epsilon. Okay. And we would like to show that this is less than epsilon, which it totally isn't at the moment. It's a little bit more than epsilon. Cursors. Okay. It seems so obvious, though.
What, use the triangle inequality?
Yeah, but I feel like we need to
You could use it in other places.
fiddle with it a little more. No, I think I've got an idea. We have to show it's less than epsilon. So if we could have the x minus c on this side, I've got an idea. Do we want x minus y? No, we don't. Just a second. Oh, I really thought it was a good idea.
If you want y minus x and you're splitting up using the triangle inequality, it doesn't matter if you have x minus y, because it's x, the norm of x minus y is the same as the norm of y minus x.
Right? Which is less than or equal to... Oh, that's going to be greater than now. It was such a good idea. All right, I'm going to look closer at my diagram. It's going to tell me what to do. I know it will. Okay? This has to work. So this diagram here, my y is somewhere in here, right? So it's not going to be a problem on the bottom end. Just need to show it doesn't fall out of here.
Couldn't you take two cases when x is greater than or less than c?
Yeah, I might have to. I was really trying not to, but yeah. Yeah. No, so, and we're painted into a corner, and so I feel like we're getting just stuck, and the greater than and less than might solve our problem. And this is the point. Like, there's a point at which you go, I can't think of anything. I'll do this because here I am in an exam and I've got to finish this proof. So and C and R, for X, B and A. So the distance, I'm just going to write this down anyway because it was part of the original information. And so we're saying that either X is more than C or it's less than C. Yeah? So suppose X is less than C. So the X is in here. And then let delta be this distance, like from here, so that we can fit our thing in. All right. And then consider that a y in there, which is in here somewhere or here. Yep. So the definition of being in this neighbourhood is that you are within this distance of x, which means that the smallest y can be is here, but not quite, right? So I'm almost there. I almost have it. Like, if y is, so I could now split into that case if y is less than x and y is more than x. Really? That's the thing, isn't it? And that's what I should have done back there. Yeah. So if y is less than x, the distance between x and y we know is less than delta. All right, just a second. So the distance, we know that the distance between, so if then we know that x minus y is less than delta. Yep. So x minus y is less than x minus c minus epsilon. And so the x's cancel, the minuses cancel. That's a c, sorry. So y is greater than c minus epsilon. Which means that the distance between y and c is less than epsilon. So which is the distance between y and c. Yes. Yeah, but just being greater than that is fine because that's the bottom end of the neighbourhood of epsilon around c. So therefore, we guess we have to show that y is less than x, but x is less than c plus epsilon, so that's okay. Also, y is less than x, which is less than c plus epsilon, because that's what it is. X is in this zone. And so therefore, y is between c minus epsilon and c plus epsilon, and so therefore y is in the neighbourhood of epsilon around c. Got it. Only 3 more cases to go.
You said that you could probably do it the last time we tried it, when we were trying to do it in 1 year.
Yeah, I'm.
Using the min, and then you don't have to do 3 cases instead of 4.
Yeah. Yeah. I mean, if y is more than x.
I think the whole point of choosing the shorter edge to be your delta is so that on the other end you don't have to do that calculation because it's definitely going to be inside the neighbourhood.
Yeah, that's right. So because you know that Yeah, but you still have to cover it, right? You have to cover all the possibilities if you're going to do the proof properly. So we could continue with all these cases, right? And do similar sorts of calculations. So it's really interesting. I was trying to do it in terms of distances, but this one was in terms of being in a certain location relative to C minus epsilon and Z plus epsilon, which is a different strategy entirely. And I'm glad that I know that now, and that you all know that now. Okay, I'm absolutely certain we can do it with the triangle inequality, but I'm not sure how. But that's one of the things the triangle inequality is for. It's like a reverse triangle inequality, isn't there, for like a subtraction? Yeah. I'm just going to give myself a little couple of minutes, continue with the cases. So the thing is, it's okay for us to have a different delta in each part of this, because the delta is based on the x that we choose. So it's okay for each x to produce a different delta, and that's all right. Okay. Yeah. I think we would have still had to go cases anyway. Even back here, we could have said, well, if y is less than x, then the absolute value of y minus x is negative. And so we get y minus x is greater than delta, and delta is whichever of these it is. Yeah, I think the cases is the best plan. Yeah. Can I do something if this is okay? Because I feel like it should reduce to this. I know how to do this in 2 dimensions, but I'm not sure if I know how to do it in 1 dimension. So in 2 dimensions, you have a ball, like it's a circle, and the distance between each point and the thing is there. And so what you do is you sort of pick a circle that is of a lesser radius than the distance to the edge of the circle you're in. And then you use the triangle inequality in here. And it's only, like, the important part of it is when it's further out. But you can't do cases here because it's round. And so we want to show that this distance here is less than the radius of this circle. Which is, we want to show that that's less than this distance, which seems to me that if we were going to use the triangle inequality, we should be... how are we going to do that? The triangle inequality needs... The thing that's smaller has to be the third side of the triangle, right? So this distance is less than that distance plus that distance, which is still too big, right? No, it's okay, I've got it. This distance we know is less than this distance plus this distance. And this distance is less than delta. And this distance is less than epsilon. But we know how much less than epsilon this distance is. It's not just less than epsilon, it's an actual distance. We know this distance. It's literally, I think I have it. I think I've got it. Okay, I'm just going to write it again. So the reason I'm doing this is that if I can figure out a strategy that I know will work, I might be able to reuse it for other proofs. So it's not like I'm trying to say this is how long it takes to prove these things, because if it did take this long, we would feel a little distressed about the exam. We're trying to figure out strategies we can reuse. Okay, so if delta is the minimum of these, it's less than both of those. Right? So, that's an important fact that we didn't use yet. Right. So, suppose y is in x so that y minus x is less than delta, right? Then the distance between y and c is definitely the distance between... That's fine. Okay? Right. Right. Okay. So, we know that this is less than delta plus this distance here. Yep. And we know that delta is less than both of these things. Yep. So, let's just point this out. Delta is the minimum. I really should have put this back earlier, but I'm putting it there now. All right, it's c minus x plus epsilon or c minus x minus epsilon, right? Or x minus, sorry, c minus x or x minus c. So this is plus or minus x minus c. Right? Yep, no, they're both, oh yeah, they're both plus epsilon, right. But this thing is x minus c, and this is minus x minus c. The absolute value of x minus c is one of those things. One of these is the absolute value of x minus c. So we know that it's one of these things, right? Depending on what x is, c is, right? And so since delta is less than both of those options, it's less than x minus, the absolute value of x minus c plus epsilon. That didn't help me. That's all right. It should be minus... Oh. Frail. I thought I had it. I really did. It was such a good idea. Wait. I just need to do it backwards. No, it's all right. So this one happened when x was less than c, and this one happened when x was more than c, didn't it? Yeah, if we're focused on that. So this one is saying that x is, like this is the distance above. No, I thought I had it. I really did. I was going to cancel out this, and this is going to come out to like epsilon minus x plus c. Which it is, right? Like x minus c, the delta, the smaller delta, is the distance, is epsilon minus the distance between x and c. I mean, that's what it's supposed to be. So this epsilon, this delta is supposed to be epsilon minus that. And so it comes out to epsilon. So maybe I should just define delta to be that, to begin with. Why don't I just define delta to be epsilon minus the distance between x and c? Right? Which we know is greater than 0 because the distance between x and c is epsilon. Oh, that's it! Right. Right. I've got it! I've got it! Yes! The world makes sense again. Okay. So we don't need any of this stuff. Like, so that's equal to epsilon minus x minus c plus x minus c, which is epsilon. And so therefore the distance between y minus c is less than epsilon, and therefore y is in the neighbourhood of epsilon around c. Yes! Right. Yay! And so therefore the entire of this thing is contained in that, and therefore A is open. Ah. Okay. I just want to redo that without all the crap. Like, I've got the picture now. So this is okay, or this. All right. So the picture was this. This is C, this is epsilon, this is epsilon. If x is here, then this distance is delta, right? That's the one we want. So we know, so we know that the distance between x minus c is less than epsilon. Yeah? Which means that there is a number, which means that epsilon minus x minus c is positive. And so we're just going to call delta this distance, and it's the distance we need. Yeah. And whichever side you're on, it doesn't matter, because you've just said it's the gap between the distance between x and epsilon, the distance between x and c, and epsilon. So it works out no matter which side you're on. And so that's nice. So we have, that's so nice. We can do this proof now, if we can remember that. If we can remember to just define it to be the leftover distance, which is what this is. Distance to the edge. Then we can do it without doing cases. Oh, I feel so happy. All right, it would be cool to like take this and reuse it somewhere. So if we had another proof that we could do, that'd be cool. I could go look. Topology is in week 7, you say?
You can do it. You can prove something like the opening from 0, 1 is open.
Well, that's the same thing, right?
Yeah. Okay.
I don't know if there's any other proofs where I could use that. Oh wow, these look a bit more complicated than something that would help for. This is open, and then we remove countably many points, so it should still be open.
This is more, that's more like intuition stuff.
Yeah. Prove that every open set is a union of open intervals. That's all right, we just choose the delta for all of them and union them all, I guess. Oh, let's prove that if you intersect two open sets, then you get an open set. Oh crap. Prove that U1 intersection U2, that U1 and U2 be open sets in R. Prove that U1 intersection U2 is also open. Okay. Okay. So if we want to prove that something's open, it means that we have to pick something in it, and we have to find a little epsilon neighbourhood or delta neighbourhood or whatever it is that's contained inside it. So how about we go, okay, let X be in U1 intersection U2, and then we have to tell the reader what delta is, and then say, therefore, or something like that. Okay. Oh, sorry, I have to tell them what epsilon is. Okay. Well, the only thing I can think of at the moment is that the meaning of being in U1 intersection U2 is that you're in both U1 and U2. And if X is in U1, then there's a little neighbourhood that's contained in a little neighbourhood around X that's contained in U1 because it's open. So there exists an epsilon 1 greater than 0 with the neighbourhood epsilon 1 of X contained in U1, and there exists an epsilon 2 greater than 0 with the neighbourhood epsilon 2 around X contained in U2.
So we know it works for each of them independently, but we don't know that it works for both of them. So we can take like them.
Yeah, because I reckon one of those neighbourhoods, they're both centred at X. One of them will be contained inside the other. And so we can say that epsilon be the minimum of epsilon 1 and epsilon 2. Then the neighbourhood of epsilon around X is definitely contained in both of these, since epsilon is less than or equal to epsilon 1. So because they're both neighbourhoods, they both have the same centre, whichever one has the smaller radius is contained in the bigger one. And I think it's okay to just say that. And that's contained in U1, and n epsilon X is contained in epsilon 2x, since epsilon is less than or equal to epsilon 1, which is contained in U2. That's bad maths writing, I'm sorry. I should probably put this since here. And I'm nearly there. Therefore, since this set is contained in both of them, it must be contained in the intersection. Oh, I can just say it. So ta-da, it's open. So, I mean, I've skipped a bit really. I mean, usually you only make that argument for individual points. You know, if y is in u1 and y is in u2, then y is in both u1 and u2. So I could actually make that little proof if I really wanted, right?
This is where you say that y is in.
So if I really, I think I'm allowed to make this argument. I think that's okay. I think it's all right. I think your lecturer would go, oh yeah, that makes sense. But if you really wanted to be really rigorous, you know, or really sure, once you had chosen what epsilon is, you could have said, say, let y be in the neighbourhood of epsilon around x. And then you can say, well, the distance between y and x is less than epsilon, which is less than or equal to epsilon 1. And so therefore y is contained in neighbourhood epsilon 1 around x, which is contained in u1. And similarly, y is contained in neighbourhood epsilon 2, which is contained in neighbourhood 2. Therefore y is contained in u1 intersection u2. Therefore this set is contained in, you know. Or if we want to be really sure, we could put this in that spot instead. Switch them out and it's the same proof. Yeah. So I think you're okay to make statements like this, but this is the really rigorous one because showing that sets are inside each other is supposed to be done one element at a time. Yeah. So is this the part of the course where you you just felt like the proofs were hard? Is that why you wanted to talk about it?
Yeah, a lot of the practice question proofs are the hardest of all of the, well, for me anyway, all of the other. I don't think it's because they're necessarily hard, I just think I'm just not used to them.
So this topology but wasn't just about open and closedness, it was also about supremums as well? Yeah. Or was that in a separate bit?
That was in the section, the real numbers section.
Oh, okay.
Yeah, this was pretty much all about open and closed.
Right.
Compact. Bound, yeah, compact.
Compact is closed and bounded?
Yeah.
Is that the definition?
No,
That's a theorem.
Yeah, it's it's like, it's really weird. It's like every sequence in a set has...
Every sequence has a subsequence that converges to a point inside. Okay. So just a second, compact would be... So, okay. So, the rational numbers aren't compact because there are sequences of rational numbers that do converge to non-rational numbers, and if something converges to a number, every subsequence converges to that number, right? And so if I have the decimal expansion of root 2, 1 decimal at a time extra, all of its subsequences converge to a non-rational number. And so it's not compact because I've found a sequence that doesn't have any sequence of rational numbers that doesn't have any subsequences that converge to rational numbers. So it's not compact. Okay, cool. And if you had just a single point, all its sequences converge to it, and so therefore it's compact. Because there's only one kind of sequence you can make. Okay. Cool. Do you have to prove the Handwritten theorem?
No.
Okay, good.
Well, I don't think so. It was a pretty long proof. It took like 40 minutes or so.
So if it was closed... Right, okay. But I can definitely prove that Right, okay. We do know there is a theorem that says that every sequence has a convergent subsequence if the sequence is bounded, right?
Yeah, the Boltzmann-Weierstrass.
Yeah. So if a sequence is bounded, so if a set is bounded, then all of its sequences are bounded, and so they all have a convergent subsequence.
And if the set is closed, then any set which converges to a
Point inside, because that's another theorem, right?
And all subsequences have to converge back to.
Yeah. So, right. So you can prove it not too short. It's not too hard to prove it if you're allowed to use those other theorems.
I think I was confusing with something else.
Yeah. So showing that closed is equivalent to every subsequence converging inside it might be a bit harder, I would say, because those are different things. So I just want to think about that. Here you go. So I don't know if you can see what I'm doing here. I'm just going to say it. What I'm doing is trying to figure out how these theorems and definitions are related to each other. Because that's what understanding is. It's the relationships between things. So until you know how things are related, you don't feel like you understand. And so that's what I'm trying to do. I'm trying to create a sensation of understanding by connecting things together. So I'm looking at the theorems and saying, okay, so just a second, there's a thing about closed and bounded, and how are they related, and am I allowed to do this? And I just keep asking those questions to see how things are related to each other. And then I feel like I understand. And then the other side of the coin is being able to have strategies that will allow you to solve problems, which is what I was doing in this one, trying to say, oh, can I make a strategy? And my strategy is I can define a number to be the leftover bit from another number. I like that. That's a good strategy that I could reuse. I might not remember it, but I can remember the picture that goes with it, and that might be a little easier. So now, they're my two strategies to try and make sense of something in pure maths in particular. I just want to give this a go, because I've still got, 9 minutes-ish. So there's a theorem, right? Which goes, A is closed if and only if every sequence xn in A for every sequence xn in A, if xn goes to L, then L is in A. Okay? I'm wondering if we can figure out, at least, maybe not proving it, but at least having an idea of why that works. So, I might put inverted commas proof. It might not be a real proof. But I'm going to make an attempt to prove it just to see if I can get a handle on how these things mean. And the only way that I can make sense of this is to know the definitions of those two things. So closed suppose A is closed, and the definition of closed is usually that the complement is open, I believe. So therefore, R without A is open. And what that means is, if I pick something in R without A, then there is an open ball, I call it open ball, that's what we call it in 3D. So there is a neighbourhood that's contained completely in R without A. Okay, so if X is not in A, then there exists an epsilon greater than 0 such that the neighbourhood around X of thing is completely contained outside A, right? Okay. Meaning it doesn't intersect with A at all. There are no points of A in that neighbourhood. i.e. n epsilon x intersection A is empty. That's the other way of saying it. It doesn't intersect with A. Okay, so that's what it means to be closed. And suppose if I want to show that every sequence that's in A that converges to something, then that L has to be in A. So I would need to say, well, let this be a sequence in A that converges to L. So I'm doing the forward bit. Suppose it's closed. Prove that every sequence that converges to something in A. So I'm going to let this be a sequence with n xn to going to L, and I'm going to have to provide reasoning that ends with therefore L is in A. Okay. Well, being open is about the outside of A. Being closed is about the outside of A. It's about R without A. And we're trying to show that something is in A, so it seems more reasonable to me to consider a set, to consider the opposite of what would happen if L was outside A, because being closed is about the outside of A. So I'm going to say, suppose L is not in A. And then that's going to form a contradiction of some sort. Okay. All right. Maybe not. First, before I make that supposition, can I please figure out what it means to converge? So to converge, that means that for any epsilon, there is... I might use delta, but so for any, usually epsilon. For any epsilon, there is an n such that for every n beyond it, it's within epsilon of L. Okay. So, okay, you're right. This is, I don't really need this as part of my proof, it's just the truth. So, okay, yes, got it. I am going to suppose this. So suppose L is not in A. Now we know, so there exists an epsilon greater than 0 with this neighbourhood being completely outside A. All right? That's what it means to be closed. Since A is closed. But it's not X, it's L that I'm talking about. Okay. And what that means is that every number that is within epsilon of L isn't in A. Right. But we also know that there exists an n in N with the distance between xn and L being less than epsilon for n greater than or equal to n. But that means, i.e., xn is in n epsilon L. If the distance between xn and L is less than epsilon, it's in the neighbourhood, epsilon neighbourhood centred at L. It's closer than epsilon to L. And this is contained in R without A, right? Which would mean that xn is not in A. Which is a contradiction because xn was a sequence in A. And so therefore, L has to be in A. We did it. Well, half of it. It was an if and only if, so we've done half the proof. Okay, so what strategy did I use to do that? Can I zoom out at all? No, only in. What are you doing? No, only in. Can I fit them both side by side to see the whole proof? Yes, just. Got it. Okay. So what strategies did I use to come up with that half of the proof? They can be as vague, or they can be mundane.
Just using the definition of
Yeah. So that was one of the big things I did. I just kept writing down the definition. But this thing here, I didn't know I was going to do at the time, but this move here where I made the decision to do contradiction was based on the definition being about things that were outside the set. And so that's I think that's a reusable strategy to say if the things that we're talking about, if the definition I have talks about certain kinds of things, then I need to arrange my proof to mention those kinds of things. So this talks about things that are outside the set. I need to talk about a thing that's outside the set, so doing a contradiction would allow me to do that. Yeah. The recording's got a little while to go, so I might try and do the other half from scratch. Okay. Now let's suppose every sequence xn in A with xn converging to L has L in A. And we want to do some working that gets us to the point of saying that A is closed. So the definition of A being closed says that if we pick anything that's not in A, then there's an open interval around it that is fully contained outside A. So again, I feel like we're going to go contradiction here, which makes me think that I could have done a double contrapositive and said that if A is not closed, then there is a sequence that does do this. That might have been easier, but whatever. Okay, so I guess I'm just going to use the definition. Let x be not in A, and then I'm going to do something, and hopefully I've got enough space, and say therefore it's contained in R without A. So I'm going to have to tell the reader what epsilon is. This one seems a bit trickier. I can't make a sequence converge to X because X isn't in A. But I suppose if this wasn't contained, I'm going to do a contradiction again. I suppose if this wasn't contained in R without A, then that would mean it would have a point that was in A. Yeah, if it's not fully outside A, then there's a piece of it that's inside A. And so there has to be, if this wasn't true, yes. So that's how you do, if I wanted to prove this right, got it, okay. So I still need to say what epsilon is, but I don't know that yet, but I'll figure that out. So at some point I say what epsilon is. I'm not sure. I have a feeling that epsilon's going to be how far away x is from the nearest point of A. Yeah. Oh, yeah! No. Crap. I don't know yet. But somewhere, once I've defined what epsilon is, I could say let y be in n epsilon x. And suppose y is in A, and then we get a contradiction, and then we'll be able to say therefore y is not in A, and so therefore the entire set is contained in the bit that isn't A. Right? So if y was in A, so we find that if y is in n epsilon x, y is not in A, and so therefore the whole set is contained outside A. So we want to put something in here that gets to that point. So if y was in A, then we could try and make a sequence that converges to it. No, what? No, I don't know yet. I'm really struggling with this direction. This seems like a good bones for the proof, but I have to use the fact that sequences that converge to something, that thing is in A. And I don't understand how I'm going to do that. I guess if I could make a sequence that converged to X, then that would make... No, that doesn't make any sense. If I could make a sequence that converged as part of my proof, if I made a sequence that converged to X, that would be a contradiction. And so maybe my contradiction is, maybe that's what's going to provide this contradiction, as long as I choose the epsilon correctly. I may decide to stop shortly. I mean, this is a proof that the lecturer probably get. I don't know if the lecturer proved this. Yeah. I did half of it. I was very proud of that half. Glad I chose that half first.
I remember what Ray went through this in the lecture. He said let epsilon equal 1 over n.
Oh. Oh, because it works for...
Because we know xn goes to L, so for all epsilon greater than 0, there exists an n such that it's within that strip as he describes it. So he said you can just pick your epsilon because you know it works for all. And then I think that epsilon also helps for the other stuff, maybe.
What's the contrapositive of this? The contrapositive is you reverse both of them, right? And the contrapositive is the same as equivalent to the original. So the thing we're trying to prove is if every sequence, etc., does that, then A is closed. So we could try and do if A isn't closed, then not all the sequences do this. And that might be a little easier, right? Because if it's not closed, then the outside isn't open, which means that which means that there is a point outside with no, there is a point outside that doesn't have any neighbourhoods around it that miss the set A. So therefore we can construct a sequence that converges to that point. Yes! Fabulous! Okay, not this. So suppose A is not closed, right? Then what we're going to try and show is that not every sequence does this. So if A is closed means this happens, and A is not closed means this doesn't happen, then it's an if and only if. Okay. Suppose A is not closed, and then we're going to construct a sequence in A that converges to L but doesn't have L in A. Right. So we're going to tell the reader what xn is, and then we're going to make one. Okay, so if A is not closed, then that means that there is an x that's not in A such that no matter what epsilon is, the epsilon greater than 0, the around x, the neighbourhood of epsilon with width of radius epsilon around x is not contained in R without A. And to not be contained in R without A means that there is a point in it that is in A. If you're not outside A, one of your points has to be inside A. I.e., there is y in this which is inside that is in both A and that. Okay, so if no matter which epsilon I pick, so in particular, if I choose epsilons to be smaller and smaller, I can therefore choose things that are closer and closer, choose things in A that are closer and closer to x. So i.e., there is y with the distance between y and x being less than epsilon, and y is in A. That's what that means. Okay. So what I'm going to do is I'm going to say, consider 1 on n. We know there exists a yn with the distance between yn and x being less than epsilon, and yn is in A. Yep. And so we'll make a sequence out of those. Consider the sequence yn, which is, yep. Now, yn is in A. Yep. And if we can show that the limit of yn is x, which is not in A, then we're good. Now, I've already used epsilon, so I don't really feel like using it again. I'll use a delta this time instead. So let delta be greater than 0. Then there exists an n in n with 1 over n is less than delta. 1 over n is less than delta. And for all n greater than or equal to n, 1 over n will also be less than 1 over n, which is less than delta. And so therefore the distance between yn and x will be less than 1 over n, which will be less than delta. for all n greater than or equal to n. So let delta greater than to be 0, then there exists an n such that yn, the distance between yn and x is less than delta, and so therefore yn goes to x. But x is not in A. So not every sequence xn in A with xn going to L has L in A, because we just found one that didn't. Thus proven. So we've done the contradiction of, proof by contradiction for the first bit and the contrapositive of the second bit, and so the whole thing works. So therefore, if every sequence xn in A with xn going to L does have L in A, then A must be closed. And therefore it is proven. Wow! We did it! I needed a little bit of help from Rave IU, but I'm not sure how much help that was. Like, it just sort of inspired me, so maybe you don't have to remember it. But we can do it. So that was a good strategy. We couldn't figure it out going forwards, so we maybe did... neither of these I could figure out going forwards totally. One of them I had to use a contradiction, and the other one, the whole thing didn't work, and so I needed to switch it up and do it contrapositive and do it backwards. Wow, that's not that bad a proof. I could reproduce that, I reckon, if I had a good night's sleep the night before. Yeah. All right, I really am going to stop now. I hope this was helpful in some way.